the scaling of the shallow water equations, and then what do we do with the scaling of the shallow water equations? We took a particular limit that had to do with what? Small Rossby number was 1/2, and what was the second part?
Product of Rossby number and the deformation radius over, spatial scale over deformation radius squared.
Yes. So L over LD was also very large. Yes. But not so large that this. Did we right? Yes. Small thing, big thing, order one thing. Right? And so that set of assumptions gave us the planetary geostrophic equations, PG equations. And the key with the PG equations is that the momentum equation is just geostrophy, but there's a DDT that comes from the thickness equation. So we were wondering before how we keep geostrophy because there's no DDT. How do we solve for geostrophy? And then we saw geostrophic adjustment, and we thought, oh, if you keep the DDT, those things propagate away quickly, but the geostrophic is left behind more slowly. But since the geostrophic still has anomalies in sea surface height or anomalies in layer thickness, in the planetary geostrophic equations, in the reduced gravity equations, maybe a system that describes the thickness of that layer together with geostrophy is a closed system. That was our sense of how we moved. And in fact, there is such a system that is self-consistent and closed, and you can solve it and you can put it into models, and it's not diagnostic. This is actually a predictive system. These are the equations. These are the necessary regime to be in to make that all work. So before we talk about QG, which is another reduced dynamic system, it's important to think abstractly, maybe algorithmically, about what the process here was. We had a sense that those kind of phenomena fit together in some particular set of scales. But it wasn't until we wrote, so this one we were sure we were on board with. We've been talking about this all semester. This one was a kind of new one, but in the blob drop experiment and the plunt versus the plunger, we started to think that this might be an important thing. And then the homework, for sure, really drives in this point, right? That how big you are versus LD has everything to do with whether you're geostrophic or wave-like, right? That's what those set of three problems based on the scale, the Fourier transform piece. It's a very nice piece of Alice to show this part. So those two are fine, but now we need a distinguished limit. Remember, I used that last time and said a distinguished limit is a limit where you make a choice about the scaling and then the answer comes out to be something sensible. This is really the distinguished limit. This says this has to be big, this has to be small, but it has to be big and small in just the right amount that this doesn't become either too big or too small. Because remember, this is the scaling on this term versus this term. So if we made this smaller, we would have had horizontal incompressibility. And that wouldn't have worked together with this. We would have lost all of our DDTs. So the distinguished limit in the planetary geostrophic equations is this, which gives us a functional set of equations in the end. Does that make sense to everybody? So the idea of a reduced dynamical system is that you're going to look in a particular regime and you still get a set of equations that make sense together. That's a distinguished limit. QG is a different distinguished limit, which gives us a different, equally sensible set of equations, and it describes a slightly different scenario than this one. Okay? So that's what we're going to do next, is figure out how to get to QG, and we'll see that it's just a little bit different from this. Okay? And the equations at the end will be a little different as well. And we already have the hint that PV is going to be important. Here we saw that this equation could be replaced with the PV equation, which in the PG equations is just F over H is PG. But this equation is almost the same as that equation, as we were discussing at the end last time. Okay, but it's important that F is not constant, because the non-constant part of F is what kills this term in the combination of those two equations. For QG, we're going to go to smaller scales than this. It's still going to be true that the Rossby number is small, but instead of variable F being the leading order critical piece and varying H being the leading order critical piece, we're going to change. We're going to have constant F to leading order, horizontal incompressibility to leading order, but then we're going to solve for PV as a correction on top of that, and that's going to give us an equation that still has a DDT in it. So it's like a perturbation theory where the second order perturbation is actually the thing that has the ability to evolve. The first order is just diagnostic relationships. Okay? Does that make sense to everybody? All right, so that's where we're going to go. So that's saying what I just said. Okay, so we go back to our scaled shallow order equations. And remember, the hats are all order one quantities, and the size of each term is pulled out into these dimensionless fraction pieces. So, okay, I could get rid of this term, and I could keep geostrophy. So small Rossby number is going to tell me that. If I have small Rossby number and L over LD has some different size, suppose L and LD are the same size, what happens to this equation?
Rossby number is small.
Rossby number is small, and also L is the same size as LD. So let's leave this up. Rossby number is small, L over LD is order 1. So from this equation we get geostrophy like we did before. What do we get from this equation? Horizontal incompressibility. Okay, and this is the equations that we stared at and thought, now what do we do? There's no DDT. If I initialize a height field, that tells me the velocity field that goes with it, but then that's it. That's the end of that's all I know. So this is the sense that we're going to go to the next order and think about what makes this system evolve. Okay? So these are the Rossby number is small, flow is near geostrophic balance, but he's saying near now, not geostrophic balance. Remember we were joking that what quasi-geostrophic means is not quite geostrophic. That's what we mean. It's not quite geostrophic. There's a little bit of ageostrophic velocity pinging around, but we haven't described it yet when we write this down. This is really, that should have a subscript G on it. These are obviously the geostrophic velocities because that's the geostrophic relation. Scales of motion are similar to the deformation scale. So L is the same size as LD, which makes this term small, which kills this and makes it just horizontally incompressible. Variations of the Coriolis parameter are small as well. So properly, we could have had F plus beta Y here, and then we would have had a slightly different velocity field that goes along with, in the planetary equations, this is not F naught, this is full F. And we saw that that was important, the variations in F were important in forming the PV out of it. So that's pinging around. This is not exactly geostrophy in a sense. This is geostrophy only with part of the F. Okay? But still, this is the leading order contribution because, so he doesn't even write it out that way, but we could write it out. F cross U is equal to F naught plus beta y cross u, and let me keep the hats on, which they're dimensionless. But at leading order, it's just F naught cross u hat, if this is small compared to that. What does this being small compared to that mean in terms of the scales of motion?
The spatial scale is smaller than the Earth radius.
Yes. So the spatial scale is smaller than the Earth's radius. This, this is a Taylor series expanded about the Earth's, with the deviations from the Earth's radius. This is also about spatial scales, but it's spatial scales versus stratification and magnitude. So LD, remember, in this system is square root of GH over F. So H is here. If the oceans were really, really deep, we could change this without changing the relationship between this. If the planet spun really fast, it would change this and it would change both of these. So that one is consistent between the two. But if the planet had a different radius, we could change the relationship between these two without changing that at all. So it's a little bit hidden. It's not just large scale, small scale, deformation scale. It's important to remember what's sitting underneath these assumptions. So QG works beautifully on Earth, sort of by coincidence, that this is small compared to this at the same time that this and this are the same size. Now, maybe it's a philosophical question whether that always happens on every planet, but on Earth it definitely works in both the atmosphere and the ocean, that there is a range of scales for which these two and this are simultaneously adequate. On Jupiter, it also works, but the relationship between these is a little different. So the bands of Jupiter are because this compared to this is actually different than it is on Earth. There's only one jet stream in the atmosphere on Earth, but in some sense there are many on Jupiter, and it's because this term is relatively larger compared to this term. Okay? All right. So, enough of that. All right. So we have these things. Okay. So now, how do I go back? What else? What do I do now if I've got these terms coming in the next order? How do I do that? What would you? So I could take the equation. Let's write the first one out because it's Rossby. F naught plus beta y cross u equals. I'm not going to write the little hats. I'm just rewriting that equation. I have a terrible piece of chalk, which is making me go slower. Equals minus eta. Okay, so if I take this first equation and I write u equals some first order plus some small correction, let's say Rossby, u1 plus dot. Everybody seen perturbation theory like this? So then Rossby squared and whatever. And then I assume that Rossby is about the same size as beta y over F naught. So that the beta term comes in at the same order. So both of these are small. I'm just saying that. Suppose, then what's the next order? So if I plug in here, I get Rossby times du0 by dt, order Rossby. So I don't need to write the Rossby U1 because that would have two Rossbys in it. It would be Rossby squared. So this is the first order from the next system plus F naught cross U0 plus F naught cross U1 plus beta Y cross U0 equals gradient eta 0 plus, oh, and sorry, I should have had some Rossbys in here. Rossby. Let me show you this way. This is size Rossby. This is size Rossby. I'm probably being inconsistent. Okay. I am being inconsistent. I'm just going to say this one is size Rossby. Rather than multiplying by Rossby, I'm just going to say this one is smaller than this one. Does everybody understand what I mean? Because I just couldn't bring myself to write it correctly. Okay, the first term, we have U naught plus a small correction. But since it's multiplied by Rossby, we can drop the small one. So this is the first term that comes out of this, which is as small as this term. Because this term has F naught, which is a big thing, times something that's order Rossby. So this term and this term are the same size. What about this term? How big is it?
As big as the gradient, the gradient of size.
It's the same size as this term. These are both big. But because we already wrote down somewhere, I didn't write down. This is the geostrophic. This is this, right? I actually am going to say that this exactly cancels that. So I have a separate equation that I've written down, this one. So both of those terms are already gone. I'm looking for the deviations from this balance in this next order equation.
Because that's the exact geostrophic part?
Exactly. So the exact geostrophic part is too big to cancel with any of the other terms. So it can only cancel with itself. So we remove it. But now, how big is this term? This term is the same size as this term by this assumption. How big is this term? Well, it's however big it needs to be to play together with these terms. How big is this term? That's where this piece comes in. And so now this could balance this could balance this could balance this. We have a full set of equations with 1, 2, 3, 4 terms in it. What if we do the same thing for this equation set? We get Rossby L over LD squared, oops, not squared again, DH dt plus big H plus eta, and eta is that same size, Rossby L over LD squared times horizontal divergence, and then we need to write this is 2 parts. Okay, so the first order is this. What's the correction? So if L over LD is order 1, that doesn't change anything, but Rossby means this term is small, too small to participate in this balance. So we can put a 0, make this, sorry, if H equals little h equals big H plus eta, and this is the order Rossby 1. It's actually order Rossby times L over LD, but that's fine. Plus dot dot dot. So this is now our correction. So the correction term appears here, eta 0. And this one we keep, but we don't have to keep it with the del dot u0. That's too big. But we keep the h times del dot u1 term. So u1 can diverge. And this one is small. This one times this one is too small. But this one times this one is okay. Does everybody understand what I'm doing? I mean, I'm probably, you may be missing some of the details, but the idea is we're trying to count all the terms that contribute at the same order. Is everybody on board with that? Okay, so if we do that, vorticity equation. One more thing we could have done from this equation was we could have formed a vorticity equation out of it first. Because it turns out, all right, why is vorticity interesting? If this is true, potential vorticity is conserved, so we're building up toward that. But if the velocity is horizontally non-divergent, then there is no gradient of horizontal velocity at leading order, right? All right, we have to erase the PG equations for a second. All right, we remember them, they're easy. Okay, if I write any old thing as a gradient plus a 2D velocity is a gradient plus k hat dot curl of a stream function, right? So I can always do this. This is the Helmholtz decomposition in 2D. So this is a scalar in this case, or if you like, it's the vertical component of the stream function. Oh, that's not writing the right way. Make that explicit. Okay. What happens if I take the divergence of this? This one's 0, so it's only this one. That. And if I take the curl, the 2D curl, whatever, it doesn't matter really. I get the curl of the curl of sine k hat, which is, there's two terms, but I'm only gonna write this one. Okay. So, when I make the vorticity equation, I don't even see this part. I don't see this potential. When I make the divergence equation, I don't see the stream function part. If I set this to 0, which is exactly what this does, I'm basically saying I don't even care about, this thing is always 0, just forget about it. So anything interesting I want to say about the u0 velocity, I can say through a stream function. So once I know the stream function, I know everything there is to know about the u0 velocity because it's non-divergent. So it looks like when you go from a velocity, there are two of these equations, but there's only one vorticity equation. So it looks like you've lost some information, but you haven't lost any information because this means that once I know the vertical vorticity, I actually know everything there is to know about the u0 velocity. Is everybody following that? The u1 velocity, on the other hand, doesn't have the u1 velocity is all tangled up in this mess. So we can't say that the u1 velocity is meaningfully described by a stream function. It probably also has a potential. We can't play the same game at the second order, but for the u0 velocity, all I need to know about it is its vertical vorticity. And because the u1 velocity is small compared to the u0, the vertical vorticity is in fact dominated by the u0, the curl of the u0, even if the u1 has one. Is everybody on board with this? Okay, so here, this one we think is dominated by u0, the curl of u0. This one is dominated by the curl of u0. This one we don't actually know. This one could have a contribution from the geostrophic part and also potentially a contribution from the u1, the ageostrophic part. And here, what do I know about this term? This is mostly U0, but what about this? It's only U1, because we know that U0 doesn't diverge. So writing it this way is a little bit complicated. It hides some of the details in this perturbation series, but it makes it much cleaner. But if we're trying to understand how these different pieces talk to each other, it's good to kind of think about them together. And what about this equation? So we've got little h here, we got little h here, we got big H here, and we got del dot. What kind of U is that? It's U1 only. So in fact, that whole math, because we already know that the part here has been, the 0th order has already been sucked out, because we guaranteed this. So the only one that survives this is U1. Okay, so we got these two equations. Now, this didn't have to happen, that both of these equations could be subsumed into the potential vorticity. But we had a hint from geostrophic adjustment that all we needed to know was potential vorticity. So let's see what happens if we form a potential vorticity equation. Okay, so to do that, first we transform all these guys to G's, which means we're throwing away now the U8 geostrophic term here, because it's small. This one is zeta G, because that's the dominant one. This one's zeta G, because that's the dominant one. This one is UA, because that's the only one that diverges. And here, this is just, this product is small, so we don't need it. This one has become UA, because UA is the only one that survives. This one is, this is just another way of writing the thickness. It's the surface height minus whatever the bottom's doing. That's just another way of writing the thickness. We don't need the big H in here. Why not?
It's constant.
Yeah, because it's constant. And in fact, there's a really subtle other approximation we're making when we're doing all this, which is related to the shallow water equations part, which is that our density layers are actually pretty flat, which is, it is equivalent to the assumptions we're making about QG building from the shallow water equations. But if you come in it in the continuous system and you're trying to write down QG, you actually have to say most of the surfaces are nearly flat. So we can't have big changes in H. Like, these guys have to be small compared to this guy. That's hidden a little in this approach, but it's there too. Okay. So how do we form a vorticity equation? Well, we multiply this one. Well, basically, if we take this particular combination of objects and expand out the derivatives, if we take the ddt of zeta g, oh, that's this equation. We take the ddt of f naught, eta minus eta b over h. F naught is constant, h is constant, so really it's f naught the constant over h constant. That's this equation. This guy looks funny in here, but it's nicely symmetric with this. And so in fact, if you're careful, you'll find that in order to get this term, I could have written plus f here, because f is constant in time, and then these two terms would have been this term on those two, right? Does everybody see that? Sorry. This, acting on these two terms, is just this equation. Yeah?
So you assume F is, oh, okay.
Time independent. Time independent. Only, yes, this is, all I'm saying is, yeah, let's write it out. ddt of zeta g is actually equal to ddt of plus f is equal to partial, if I take the partial of f, it's 0, zeta g plus u dot grad zeta g plus f. So this one plus this one is equal to that. Everybody got it? So really, this is just this equation, and this is this equation times f naught over h. So what happens to this and that? Where do they go? They're not in this equation. They cancel, because it's got a minus sign up here, and if I divide this by h and multiply by f naught, it gets a plus sign. So I'm basically just adding those two equations together to get this one. Yeah.
But in equation 5.22, we have on the right side that we have order Rossby, but on the left side we have order 1.
In which equation? Sorry, this one?
5.22.
5.22. Oh, no, careful. This is coming from this term, which is order Rossby.
Oh, okay.
This is also order Rossby. Even this one is order Rossby because F meridional gradient is small too. This one is order Rossby because order 1 has divergence equals 0. So it's Rossby, 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 Rossby. This one is also Rossby, 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 Rossby. We add them together, we got Rossby, 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 Rossby. What we don't have is we don't have the form of PV we might have expected to get. Why don't we have this?
This is the linearized potential.
Linearized in what? What is the small parameter that we linearize from this to get that? Small Rossby. If I write this out as zeta G plus zeta A plus F naught plus beta Y over big H plus eta, and then I Taylor series. The first term I get is zeta A over big H. This is it. Big H comes out and cancels out because it's 0. The second term I get is F naught over H. That one's actually gone because it doesn't matter whether, it's written here, but it actually won't do anything because it doesn't have any derivatives. F naught over H. But beta Y over H is a non-zero term that comes in. That's, both of those are hiding in here. And what about this crazy thing? That's the Taylor series for this being small compared to that, taking only the largest term in the numerator, which is F naught. Does everybody see how that works? You know, like if I do 1 over x plus delta x, that's equal to minus delta x over x. Did I do that right? No, I did not do that right. Let me write this as something else. Constant. Constant. Does everybody see what I'm trying to do here? I'm trying to write, did I do it right? Squared. Okay, there we go. Now I've finally gotten it. So this is the Taylor series. If you have the small quantity in the denominator, you have first, just ignore the small quantity, then a minus sign, the small quantity in the numerator, and double the size. That's the relationship between this over this goes to this over this. Yeah.
I feel like the potential vorticity there and like the one in 5.25 are not of the same unit.
Yeah, why not? So, as I said, zeta A over H, this is zeta G. Since H is a constant, they've just pulled it out and thrown it away. So, yes, quasi-geostrophic potential vorticity does not have the same units as shallow water potential vorticity. Because in shallow water, you had to have divided by thickness in the denominator to make it work. Here we didn't need it because it's divided by a constant thickness, so we just throw it away. It's extremely confusing, and I would actually prefer if they wrote the big H underneath. It would not change the meaning of this equation at all to divide this by big H and this by big H and this by big H squared. It just would give it the same units. Likewise, you know, F naught over big H, we don't actually have to have F in here. We could have just written beta Y. And so Pedlosky writes beta Y and throws out the F naught part, which is even weirder because it's saying that the biggest term is neglected, but it is neglected because it's constant. So it's all because it's inside this operation that they do this. And it's sort of tradition to throw those terms out. But if you want to understand why, it's hard. Yes. And potential vorticity actually is not conceptually is not something that has fixed units. It's always something that's conserved, a thickness equation in this case, and a vorticity equation. But this could have also been buoyancy or temperature or chlorophyll even. And we could have written a potential vorticity out of it. It's just the idea that the stretching and squeezing of layers counterbalances the spinning up and spinning down like a ballerina. Does that make sense to everybody? Sort of. Everybody, right, whatever, doesn't matter. This is the same as this in linearization. To leading order, that is the same equation as this. So this is the potential vorticity equation, and it combines some information from these two. Is that enough to solve the whole system? If we know this, and we know this, and we know this, is that actually a closed system? Yes. Oh, sorry, that's the part about PV. In fact, it is. Here is dq dt, where the advection is coming from this. The only thing I'm advecting with is the vorticity equation. So if I have a stream function that gives me a velocity and a stream function that gives me a velocity, that gives me all of the geostrophic advection in this. So I'm taking the QGPV, I'm advecting it with the geostrophic velocity only. Don't have to advect it with the ageostrophic velocity, because the ageostrophic velocity doesn't appear in this equation. It got thrown away. In fact, I don't even have to know what the ageostrophic velocity is, because it canceled out between these two equations. I can go back and find it if I want to know what it was, because I can always calculate the vorticity equation or the thickness equation once I know the rest of the terms. I know everything about this term and I know everything about this term, then I can calculate that. So how do I get those pieces? Oops. I mean, this one in the middle is not helpful. I can do it because I can invert. Once I know Q, I can find psi and A to B from this complicated, or A to B I know that's topography. I can find psi from inverting this system. Everyone understand what I mean by inverting? You give me a Q, I can tell you what psi is. It's a little bit of work. I have to invert a Laplace equation, or yeah, but I can do it. Or actually it's a Helmholtz equation when you put these two equations together. Does that make sense to everybody? So how do we solve this system? You say, okay, give me a PV field, just like in geostrophic adjustment. Calculate the PV field everywhere. How is it going to move? I know I'm going to evolve it like this, but how do I get the velocities? Okay, write this equation down. Given Q, solve for psi. I'm given this because I know how big the planet is and I know where I am. I'm given this because I know what the bottom topography is. So everything in this, everything here is known except for psi. Do that with some boundary conditions on psi, like rigid sidewalls or periodic domain or whatever you want. I can solve, now I've got psi. Now what do I do with psi? I go down here and I say, I know that psi is related to the pressure. I know that psi is related to the pressure. It is also related to the geostrophic velocities. I can calculate them this way. That's what's going to do the advection. Geostrophic velocities advect your Q. Now you have a new Q. Play this game again. Okay? So in the geostrophic adjustment problem, we did this, but we had one big simplification, which is we linearized this equation, which meant that we didn't actually move the Q, we just left it where it started out. In this, the nonlinear quasi-geostrophic equations, the Q is going to move based on the velocity field we find from inverting from the potential vorticity for the stream function. So this is one step more complicated than the than the geostrophic adjustment problem in that it's nonlinear because we're actually allowing the Q to, we didn't have the linearized QG equations are what we use for geostrophic adjustment. This is the nonlinear quasi-geostrophic equations. And the amazing thing is there's only 1 degree of freedom. The only thing we have to know is Q. And everything else comes from that. Because we started with a, Boost and S system that had U, V, W, pressure, density, 5. And then we went to shallow water equations, which has U, V, and H, the other 2 dropping out because of hydrostatic balance. And now when we go to QG, we just have Q. So we have gotten a lot simpler by doing that. And what were the governing variables, the state variables in planetary geostrophy? This is the good quiz question. QG is Q. What was it in planetary geostrophy? We'll go back. What's the thing that moves here? What's the thing that evolves? H. Once I know H, if I know the bottom topography, I can figure out eta. So that's just a diagnostic relationship. Once I know eta, I can find out U and V, the diagnostic relationship. That's it. So if I know H, I know everything. All I have to do to initialize this system is give me an H. QG is the same way. All you have to do is give me a Q, and I can evolve the system the same way. So in these geostrophic systems, we've gone from 3 degrees of freedom in shallow water equations to just 1 degree of freedom. And we lose a lot when we do that. QG equations don't have everything in them. What do they not have that I've already talked about? The QG system doesn't have everything that the shallow water equations have in them. What are some of the things we've talked about that get removed in this process? Think about geostrophic adjustment, for example. The gravity waves. So the 3 degrees of freedom and the Rossby and the geostrophic adjustment problem, 2 of them were just the waves propagating away, and then what was left over was the geostrophic flow that was left behind. So we've totally removed those. There are no gravity waves in this system. You can plug in and try and get them. You won't find them. There is no signal here that propagates at speed square root GH. Which is fascinating. Whatever. This is a closed system, so it's another distinguished limit. It's a useful set. What else do we get? This is maybe more subtle. What did we lose by linearizing the PV from this version to this version? This is a super hard question. I don't think there's anything with this. All right, I will give you the answer to this one because this one is super hard. Look at this. If I flip the sign of the stream function, so go from a cyclone to an anticyclone, it flips the sign of the PV. So beta Y, and these parts removed, not worrying about the planetary piece. The perturbation away from the planetary and bottom topography contribution is symmetric between cyclones and anticyclones. Does that make sense? This is linear, and so therefore symmetric. When we go back here, here's my geostrophic, here is my sea surface height. So if I have a high, an anticyclone, this is a positive number, this is a negative number. And if I have a low, this is a negative number, this is a positive number. They're not symmetric because of the product. If I change the numerator, I'm changing the denominator in the opposite way. But when I linearize like this, I've lost that covariance of top and bottom. It would be the next term in the series, which is whatever it is. 1/2. It would come in there. Okay? So, that's just a slight warning that QG doesn't have everything we might want to have in it. All right. So, the only piece that we have left to do is to go back and run through these games again in the continuous limit and then the Ekman piece. So, I'm going to leave the Ekman piece until Friday. We'll start talking about that a little bit. You can take a look at those. Some of the Ekman stuff is coming in the homework, but that's not due till next week. So we'll see. We'll go over those pieces on Friday. So Friday we'll discuss the homework 2, the reviewing process, if there are remaining questions about those problems, and then we will, after you've taken a look through the key and everything, and then we'll finish off these last 4 slides of this. Does that make sense to everybody? Next week, we start talking about turbulence. No, instabilities. So instabilities are the pathway to turbulence. It's the thing that these equations are good. The nonlinearities in these equations actually allow things to spontaneously emerge from like a steady uniform flow. So that's what an instability is. We want to have a sense of that. That's the pathway to turbulence. So you squirt, a hose, and by the end it's broken up into droplets. That's the kind of process we want to think about a little bit. And then those droplets would become turbulent in the right conditions if the hose spray was long enough. That's where we're headed. Does that make sense, everybody? All right, cool.